Okay, I'm going to make a start. I don't really understand why the light is not on today. It does say it's recording down here. I don't understand why there's only one screen, so please bear with me. You'll just have to look over here. So today we're going to be talking about problem solving and search. So this is the traditional AI part of the course, if you like. So in particular, we're going to define problem solving agents, types of problems, how we go about formulating a problem, give you some examples, and then we're going to talk about some basic search algorithms. So some of the basic search I suspect may be familiar for those who've done advanced data structures and so forth. Please bear with me if it is familiar. It's not going to be familiar to everyone. We may not get through all the material in this lecture. I'll roll it over into Wednesday's lecture when I'm going to carry on talking about search techniques, and in particular introduce the most famous traditional AI technique known as A-star search. But we need to build up to that. So remember that last lecture we talked about the nature of agents, and so now we're going to define this slightly more general but still quite restricted form of a general agent. This is our problem-solving agent. And so in particular we've got a bunch of, this is effectively the memory of the agent, the sequence, so this is just an action sequence. Initially this is going to be empty, the things that the agent is going to do, the state of the world that the agent is able to observe, we hope, a goal, probably initially null, and then the agent is going to decide what the goal should be, and then a problem formulation. So this very, very general statement. In a sense, this is the process that we would go through as designers, creating this agent. So, so first of all, we update the state depending on what we perceive of the environment. So that's the first thing we do. And then if the current set of actions is null, then let's have a think about what actions we need to do. So first of all, we're going to formulate a goal. Then, having formulated the goal, we'll formulate the problem. Then we're going to do some search over the problem to find a set of actions that hopefully is going to get us to the goal state. So that's going to give us a sequence of actions, and then we're just going to perform the next action as recommended in this sequence of actions. And this function here, remainder, is really just saying remove the front action from this sequence of actions and return us with the rest, so return the current action. So this is offline problem solving, and I'll try and make this a little bit more concrete with examples during the lecture. But effectively what we're doing is executing the solution with our eyes closed. If we're going to go to, so there's a restricted set of problems for which we can apply this technique. If we're going to something that's online, where we've got online sensing, then we need to act without knowing full knowledge of the environment. Yeah? What happens if the environment changes before you do it again? Well, so then you end up and you have to do online problem solving. Okay? So then you're into a much more complex scenario, and we'll come to that later in the course. So here's an example of setting up our problem-solving agent, and this is an example that's again taken from Stuart Russell's book, and it's deliberately chosen. Are there any Romanians in the lecture theatre? Okay, so that's good. Probably it means that if you are on holiday in Romania and you're currently in Arad, how many of you would know how to get to Bucharest? Okay, that's good, because you can think of yourselves as being the agent in the absence of any other knowledge. But perhaps we're in Arad because we want to top up our suntan, or because there's something particular in that city that we wanted to see. But so we need to formulate a goal. Now, a goal might be see more of the sights of Arad, or it might be eat more of the nice food there, or it might be top up our suntan, or something like that. But perhaps It's that actually our visa is about to expire and we better get to Bucharest because that's the only place that we can get a flight out of the country. So that's our goal formulation. What is the thing that is most important to us at the moment? So perhaps it's that we have to be in Bucharest so that we can get a flight tomorrow. So how do we go about formulating the problem? Well, in this particular case, we're going to talk about abstraction of problems. So the way we might abstract this particular problem, to formulate the problem, is to come up with a set of cities, and we have a way of getting from one city to another via highways or via trains or so forth. And we have a set of actions available to us, and those actions might be get on a train to go from city A to city B, or get in a car to drive from city A to city B. What we certainly can't do is just go in a straight line from Arad to Bucharest, because we are not crows. So we formulate the problem in this abstract way, moving from one state to another, where in this case one state is a city and we move from one city to another, and eventually we hope to end up in Bucharest in time to get our flight tomorrow. So our solution to this problem, the solution that the agent is trying to seek, is a sequence of cities, or in fact a sequence of actions that will take us from one city to another. So actually here this is not strictly true. What we really want is the sequence of actions that are going to get us from one city to another. If you didn't have a map available of Romania, so if like me, and I guess everyone else in this room, you're not Romanian, you don't really understand Romanian geography, but perhaps you're in Arad, and what you can observe is that there are 3 highways, and they are signposted to 3 different cities. Perhaps the only option that's available to you is to explore each one. And perhaps by the time you get to the next city, you'll be in a position to find out, am I closer or further away from my goal? Have I gone in the right direction? So you've got to do a degree of exploration. If, on the other hand, we have a map available to us, then perhaps we can be a little bit more informed about the way we tackle this problem. So up here, here is Arad, and down here is Bucharest, and I guess most of you can look at this and see, well, actually, going in roughly a straight line is probably a sensible thing to do. Now, anyone like to suggest, is this the best path to take? How would you find out if that's the best path to take? Sorry? Well, exactly. So in this particular case, we can see fairly clearly that getting from there to there that's a shorter path than the other option of going this way. Perhaps the really important thing that we need to do, or the thing that is not immediately obvious, is 211 plus 99 greater or less than 80 plus 97 plus 101. I suspect that this is going to end up being the shorter path than going in that direction. Maybe in a more complex version of this problem, we might add on time to get through cities. Perhaps the time to get through these 2 towns here might outweigh the fact that these 2, the distances travelled, is in fact further away. Or maybe there's no fuel station here and we might have to get fuel there. There might be other things that we factor in. We're not going to in this particular example. So the types of problems that we're going to deal with in the first instance. First of all, a deterministic, a fully observable problem. Okay, so in that particular instance, we know what state we're in, and we know the effect that any action is going to take, how it's going to transform us from one state to another. So the agent knows exactly which state it's in, and the solution is a sequence of states. And I'll go through some more concrete examples of this. The other types of agents, or problem types, sorry, that we're going to talk about, suppose the environment is not completely observable. Perhaps, for instance, we don't know what state we're in at a particular moment, or in particular, we don't know what state we're in when we initialize. Then that leads to what we call a conformant problem. Still, the solution is going to be a sequence, and even if we don't know what state we're in, sometimes it turns out that we can solve the problem still quite efficiently. Non-deterministic and partially observable environments, we have what's called a contingency problem. So that's what Kieran was referring to. Suppose we have a dynamic environment that changes, and percepts will provide us new information about our current state. So we need to be able to sense the environment as we go along to be able to update what our next best action might be. We can't plan ahead to get to our goal and guarantee that we'll get to our goal, because there may be things that change. Maybe in this navigation example, perhaps the environment changes because there are roadworks, and that changes the cost, traffic jams and so forth, yeah. So the solution in this particular case is not a fixed sequence of actions, it's a contingency plan or a policy. So the policy is the thing that tells us what action to take next. It's not giving us a fixed sequence of actions, it's effectively an algorithm or a method to tell us how to choose the next action as a function of the current state we're in and what we're currently observing. So quite often what we'll do is we'll interleave search and execution. We'll search for what we think might be the next best sequence of actions to take one of those actions, and then take a step back and say, has that actually improved our situation or not, according to the current state of the environment. And then finally, an unknown state space. So this is something that's much bigger. An example might be, if I want to draw from work that I do, I think I showed you a video of online mapping of a camera. So perhaps as a stereo camera moves through an environment, perhaps its goal is to explore all of the environment and build a map of that environment. But it doesn't actually know what the environment looks like before it even starts. So it's exploring, and it's perhaps finding new places that it can go, and the state space is the space associated with that entire map. So as it explores further, the state space increases. We don't have a fixed state space. So let's start with this really simple example of the vacuum world. So remember, in this vacuum world, we have a robotic vacuum cleaner and 2 rooms, and the state of each room can either be dirty or clean. So that means we can enumerate. This is a very, very abstract version of the robot vacuum cleaner. We've abstracted an entire room to a single state. We've abstracted away the movement of the robot from one room into another, into move left, move right. Whereas in reality, the robot might have to do all sorts of navigation to get itself to a door, through a door, and so forth. And we've abstracted the notion of clean carpet and dirty carpet to simple binary state, clean or dirty, whereas in reality, dirt could be spread around, or there may be different quantities of dirt, and so forth. But that's one of the things that you need to do. The art of building your agent is to come up with an abstraction that is simple enough to deal with, but complex enough to solve the problem that you're interested in. For the purposes of the real world, this is probably not a complex enough abstraction of the world to be particularly useful, but it is useful as a pedagogic tool. So that's why we're using it, not because anyone would genuinely build an agent this simple, or an environment this simple. Okay, so we can enumerate all possible states that this entire system could be in. Here they are, up here, 1, 2, 3, 4, 5, and so on. So the odd-numbered states are the ones where the robot is in the left-hand room. The even-numbered states are the ones where the robot is in the right-hand room. And then notice that up the top we've got both rooms are dirty. Here we've got just the left room is dirty. Here we've got the right room is dirty, and here neither room is dirty. So the reason there's 8 states, it's 2 to the power 3 possible configurations of the world, if you like. So what's a solution? Well, presumably the goal is that we want the world to be clean. That's a fairly obvious goal in this case. So what's the solution in this case? Remember, we have a set of possible things that the robot can do. It can suck, it can move right or left, or it can do nothing. Obviously, doing nothing is not going to help the situation at all. If we start in state 5, Anyone want to volunteer what the solution is? Yep. Absolutely. Right suck. There we go. Right suck, and that's because the robot will move to there and then it will suck. And we're assuming that it perfectly sucks every time. So as soon as it's executed that one motion and done suck, we know that the world is clean, we've satisfied the goal. Okay, so now for a conformant problem, let's suppose that we don't know where we are. It's still possible to solve this relatively straightforwardly, perhaps because it's such a simple problem, without knowing where we start. And we're going to rely on the fact that moving left when we're already in the left-hand room will do nothing, moving right when we're already in the right-hand room will do nothing. So, anyone want to propose a solution to this one? Yep.
Move right, suck, move left, suck.
Yep, okay. Why is that the answer?
Oh, so move right twice at the start. Oh, no, because that's...
No?
Move right once, and then
No, you're absolutely right. So, move right once. If you started left, then you're now guaranteed to be in the right-hand room. If you were already in the right-hand room and you move right, you're still going to be in the right-hand room. So then you suck, then you're guaranteed that the right-hand room is clean, then move left, suck, guaranteed that the left-hand room is clean. Okay? So there you go. Move right, suck, move left, suck. And you could change the order of those too. And if you started out in the right-hand room, moving left and then sucking, moving, and so on. Okay, so for a contingency problem, let's suppose we're guaranteed to start in 5, but perhaps we've got a defective vacuum cleaner that occasionally, even when the floor, or if the floor is clean, it will accidentally leave dirt for some reason. We're not going to go into why that might happen, but so we're going to rely on Murphy's Law for that. So the action suck can dirty a clean carpet. So the way around this is we're going to have some local sensing. Otherwise, we can't ever solve this problem. Because we can't guarantee, we could just keep moving left and right and sucking and never knowing whether the environment is clean or not. So we're going to need the ability to sense whether the location is dirty or not. So there's a solution to this particular one. Move right, so we're guaranteed to start here, move right, and if it's dirty, then suck. So can you see why that's a solution? If it was just right, then suck, then we would be okay if we really are in this state, I guess. But suppose we were in this state down here, in state 7, and we moved right, there's a chance that we might have just soiled that carpet. Yeah?
If suck can dirty a carpet, then wouldn't we have to make sure that after we suck, we check the carpet again to make sure that the previous suck didn't redirty?
Okay, so the devil is in the detail here. Suck can dirty a clean carpet, but suck won't, in this particular contrived example, suck won't fail on a dirty carpet, okay? Okay, bit contrived. Okay, so a problem in general is going to be defined by 4 things. It's going to be defined by the initial state, a successor function, a goal test, and the path cost. So the initial state is, in the Romania example, where we are, or in the robot example, the room that we're in and the state of the world. The successor function is, we're going to call this S, and X will be the current state. What the successor function does is it returns to us a list, a set of all possible actions and their consequences from that state. So in this particular example, the way I've denoted this, Arad to Zerind, that's the action of driving on the road to Zerind from Arad. So that's our action, and that's the consequence, the final state given that action and the initial state. So the initial state is Arad, the action is drive from Arad to Zerind, or drive on the B75 perhaps. So it's not necessarily going to have these two names in here, drive on the B75 and the end state is Zerin. So the goal state is, have we completed the task that we wanted to complete? For example, have we arrived in Bucharest, or is there no dirt in the environment? And then the path cost, typically the thing that we're going to use to measure how efficiently we are managing to achieve our goal, might be something like the sum of the distances. So if we're travelling from city to city, sum up how many kilometres we've had to travel. It might be the number of actions that we have executed. We're trying to solve an 8 puzzle or a Rubik's Cube in a minimum number of moves. Then perhaps we're counting the number of moves that we had to do. So we're going to define the step cost. So this is the cost of each step that we take. We'll assume that it has to be greater than or equal to 0. And we'll call it C, where X is the state that you start in, A is the action that you perform, and Y is the state that you end up in. And C is the cost associated, or the path cost associated with that action. And then a solution is just a sequence of actions leading from the initial state to the goal state. Okay, so I talked earlier about abstraction, so maybe I'll go through this fairly quickly, but the real world is absurdly complex. There's just, we can't possibly search the entire real world. So we have to abstract our state space to be able to make it tractable for some kind of problem solving. So, our abstract, so a particular abstract state is going to represent a set of real states. So, for example, in the city, our abstract state might be that we are in the city of Arad, and we're abstracting away all the detail that we might be on a particular street or at a particular GPS location. We're just going to represent that we are in the city, okay? So that's an abstraction of a state. An abstraction of an action is going to be, the real action could be incredibly complex. It could be that we've got to go to the rental car company and pick up a car. Once we've picked up the car, all the intricate driving instructions that we have to give, turning the steering wheel left, right, so forth, applying the brake, all of these things, ridiculously complicated and don't necessarily help us particularly in understanding the problem that we're really interested in. So what we're going to do is we're going to abstract away that as a competence that we'll assume that some other thing can take care of, the act of driving from Arad to Zerin, for instance. And the solution, of course, is going to be some abstraction as well. We're in Bucharest. Perhaps the detail is that we actually want to be at the check-in desk of our EasyJet flight to Heathrow, for instance. So the set of real paths are solutions in the real world. But our solution is just going to be a set of cities, for instance. Pretty clearly, an abstraction should be easier, or in some sense more general, than the original problem. So here is the state space graph of the vacuum cleaner task. So what you've got, remember we had 8 possible states of the world. Here are the 8 possible states of the world. And now what I've done is I've drawn arrows from each of the states to the corresponding state that results from a particular action. So what I've got here, each arrow represents a particular action. Starting from here, if I'm up here and I perform the suck action, that takes me from this state here where both rooms are dirty to this state here where only the left-hand room is dirty. The robot obviously is still in the right-hand room. If I then move right from this state, then I stay in exactly the same state, which is why there's a loop here corresponding to the move right action. If I perform the suck action, well, in this particular case, I'm assuming that sucking a clean floor doesn't result in dirty. We've gone back to the simpler version of this problem. So I stay in this particular state, and so on. So hopefully you can see that this state diagram tells me. Have you encountered state diagrams in any other part of CS? I see 1 or 2 heads nodding. Yep, good, okay. Right, so in this particular case, the states are just the dirt, which is a binary flag, 0 or 1, and the robot locations, again binary, left or right in this particular case. The actions, 4 actions, maybe just 3 actions, because no-op is not a particularly useful action in this context. The goal test, no dirt. And the path cost, well, perhaps in this particular case, the cost of performing any particular action will assume just to be 1. So we're abstracting away all the complexity of the individual actions of moving from one room to another and vacuuming and so on. Okay, slightly more complicated example. Occasionally crops up in tutorial questions and exam questions, and that's not suggesting that it will this year, just that it has in the past. So the 8 puzzle, you're probably all familiar with this. Anyone not encountered the 8 puzzle? Sort of a primary school thing where you have a bit of plastic, and rather than it being numbers, typically it would be a picture or something, and you jumble the picture up, and then you want to move these, and you can see that the only possible moves at this particular state are for 2 to move down to here, 6 to move left, 5 to move right, or 3 to move up. So you've got a limited set of moves, and you'd like to reconstruct the picture, or in this case, get the numbers back in the order 1, 2, 3, 4, 5, 6, 7, 8. So the states in this particular example are the integer locations of the tiles. Okay? So we can just write a list of 8 numbers, where the first number represents the position of tile 1, the second number represents the position of tile 2, and so on. So that's a way of enumerating all the possible states of the 8 puzzle. The possible actions. Well, a nice way of abstracting the actions, I said the possible actions are you could move 3 up, you could move 6 to the left, you could move 5 to the right, you could move 2 down. Well, depending on the configuration, of course, it's not going to be 2 that moves down or 5 that moves to the right. It could be 7 that moves to the right. A nice way of abstracting this is to think about moving the blank. Of course, physically you don't move the blank, but this is just an abstraction. So if we were to move the blank left, in effect, what that means is that we're going to swap 5 and blank, which we're allowed to do. We physically affect that by sliding 5 to the right, but the effect is to move the blank to the left. Moving the blank down is exactly the same as moving 3 up. So it's quite a nice abstraction that we only ever operate on this one thing. We only ever operate on the blank and move it up, down, left or right. So the goal state, pretty clearly, I've already told you what the goal is. The goal is to get all of the tiles in that order. And the path cost, again, it makes sense to think about the path cost as just being one move. Actually turns out that the optimal solution of the n puzzle, so 8 is this small 3x3 version. If you go to a 4x4, then it's the 15 puzzle, 5x5, 24 puzzle, and so forth. So optimal solution of this is NP hard. Okay, so a more complicated example. Suppose we're doing robotic assembly and we want to help get our robot to help us put our IKEA flat pack together. Not so far-fetched, not possible yet with current technology, but some of my colleagues at QUT are working on exactly that problem. Can you get a robot to help you put together an IKEA flat pack? Okay, so the states of the world are presumably going to be the real valued coordinates of the joint angles of this robot and the locations of the parts that we're trying to assemble. The actions available to us are going to be the movement of the robot. So how can we apply either force or acceleration or velocity or position control to the joints of the robot? The goal test is clearly going to be we've assembled the thing that we want to assemble and we've moved the robot out of the way, and maybe the path cost in this case is the time to execute. How quickly can we do it? But maybe it's not time to execute. Maybe it's energy consumption, or maybe it's do it in the quietest possible fashion. time might involve really aggressive motions of the robot that are noisy and potentially dangerous. So perhaps we want the smoothest possible motion of the robot so it doesn't stress its joints and doesn't make a lot of noise. Okay, so how do we go about solving these problems? And I've already alluded to the fact that we're going to do it using search. And in particular, tree search is a standard way of doing this. So the basic idea, pardon me, I don't know why I've got a funny... So the basic idea is that offline we're going to do some simulated exploration of the state space. And we do this by generating the successors of already explored spaces. So I'll try and make that a little bit more concrete in a second. But so here's the general function of tree search, and we're going to unpick some of the parts of this tree search and look into some more detail. And again, if you've done advanced data structures and so forth, you've probably looked into different kinds of tree searches. How do you construct a tree? How do you go about searching it? But in general, in AI, we're thinking about a problem and a strategy to solve that problem, and our tree search, we hope, is going to return a solution to the problem, or tell us that it was impossible. So we initialize the tree search using the initial state of the problem, and then we're just going to loop. And the loop is, if there's no candidates for expansion in our tree, no further actions that we can take, then we'll return failure. We haven't succeeded in reaching the goal state. Otherwise, we're going to choose a leaf node for expansion according to some strategy. So the strategy will tell us which node to choose. And different strategies will result in different kinds of search for the tree. So we choose that leaf node. If that node happens to contain a goal state, then great, we've succeeded. We've found a solution to the problem, and we can return it. Otherwise, we're going to expand that node and we'll add those resulting nodes to the search tree. And the order in which we add those nodes also will tell us something about the search algorithm. So we've started out in Arad, and I told you, and you can probably see from the picture up there, that there were 3 roads leading out of Arad. So these are the 3 roads. So the first thing that we do in our tree search is we check, are we at our goal? Quite clearly we're not in Bucharest, and so the next thing that we do is we say, are there some actions we can take? Yes, there are. There are 3 roads leading out. Let's think about what each of those 3 roads, each of those possible actions will do. And they will take us either to Sibiu, to Timisoara, or to Zerind, and apologies to anyone who speaks Romanian if my pronunciation is really terrible there. So we've expanded these 3 nodes, and now we check those nodes, or we check one of the nodes to say, is it the goal state? So in fact, we go to here, and we say, so we go to Sibiu, we say, is this the goal state? No, we are not in our goal yet. Is there anything that we can do from this state? Well, yes, we can go back to Arad, we can travel to Fagaras, we can go to Oradea, or we can go to Râmnicu Viola. So there's 4 possible paths out of Sibiu. So we'll expand each of those, and so on. Okay, so that's the general structure of the search, and now we're going to well, in a second, we're going to look at particular strategies that we might take. First of all, one caveat, if you like. You guys are the implementers. We're talking about abstract states of the world and so forth. And I want you to distinguish between the implementation in the tree and the state. So the node of a tree is a data structure that tells you what state you're in, but it also tells you a whole bunch of other stuff that's really important from an algorithmic point of view. So the node of your tree tells you the parent node, tells you where you came from. It typically will tell you its children or its potential children. It will perhaps tell you how deep in the tree you already are. And it perhaps will tell you what is the cost, and I'm going to represent that by this function g of x, where x is the node. G is the cumulative cost to get to this particular point in the tree. So our representation up here of a node has things like, well, the path cost to get here is 6. It's 6 deep in the tree. It's got some parent nodes, and we reach this particular node from that parent via a particular action. So those will be the things that we want to represent in our tree, and one of the things in this node, obviously, is the current state of the world. States themselves don't have parents, don't have children, depth, and so forth. So the expand function, if I go back to here, we have this expand function down here. Let's make that a little bit more formal. The expand function is the thing that's going to create new nodes, and in the process of creating those nodes, it will fill in the various fields that we're interested in. So when we expand, we know what the depth is, we probably know what the path cost is, we know what the parent was and what action was to get us there. And maybe we have to run successor function to understand what the new state is. So here's an implementation of a general tree search. Okay, so we have our problem, and this thing here, fringe, is representing the set of things that we're currently considering, the set of potential actions or states that we're currently considering. And what this tree search will return is a solution or the impossibility of reaching a solution, some kind of failure. So the first thing that we do is we add into the fringe, the set of active nodes, if you like, the initial state of the problem. Okay, so we're going to create a node corresponding to the initial state of the problem, and we'll insert that into the fringe. So that's like expanding the very first node. Then we just have this loop here, this infinite loop that says if, well, this will loop infinitely until we hit one of these returns, of course. If the fringe is empty, that means that we haven't reached the goal, but there's nothing further to do. So this must indicate failure. So we'll return failure. Otherwise, we're going to take one of the nodes out of the fringe via this remove front function, and that will become the current node. And we'll look at the current node by testing to see if the node satisfies the goal state of the problem. So we want, for that, we want to know what state this node corresponds to, and is that state a solution, a goal of the current problem? If so, then we'll return that node. We're done. We've solved the problem. Otherwise, we're going to insert into the current fringe all of the children of the current node. So that's what this function expand does. It takes the current node and expands it via all of its children using the successor function. So here it is up here. Function expand returns a set of nodes. Start out by saying that successors is the empty set, and we're going to increase the size of that set in this loop. So for each possible action and result that is returned by the successor function, so the successor function gives us all of the new states and how we reach them. So we're going to create a new node S, and the parent node of S is the node that we started with. The action to get to S is the action that we used that's been returned by the successor function, and the new state is the state that the successor function tells us we will be in. So this is populating a new node that we've just expanded. The path cost to get here is going to be the path cost to get to the parent node plus whatever it costs us to get from parent node to the current node via the action that we're considering, and the depth is just increased by 1. So this populates all the fields of our node in the tree. Then we just add that to the successors, and we do that for all possible successors and then return that list up here. So that's what insert all does. So a strategy, talked about search strategies, a strategy is defined by picking the order in which we expand the nodes. And we can evaluate these strategies according to various different criteria. In particular, we can say, is a search strategy complete? Meaning, if a solution exists, i.e. if we can get to the goal, will we actually find it using this particular search strategy on the tree? Not always guaranteed. You might think that you'll always find it. If it's there, you won't necessarily, and I'll show you some examples where you may not. Clearly, and you would know with many computer science problems, we're interested in how much time does it take, and in particular the complexity. How does it scale with, how does the time scale with the size of the problem? And the space complexity, how much memory is this going to use as a function of the size of the problem? And then this last one, optimality. So completeness and optimality are not quite the same thing. Completeness says, will it find a solution if one exists? And optimality says, will it find a least cost solution? So there may be multiple ways of getting from Arad to Bucharest, and our search strategy might give us one that actually takes an awful lot longer to get there, or we have to travel an awful lot further. Ideally, we'd like a strategy that gets us there as quickly as possible, or with as little effort as possible. And so optimality will measure that. And we can measure the time and space complexity in terms of various properties of the tree. B, the branching factor of the tree. So how many nodes are we typically expanding in this function here? How many nodes are we typically expanding? That would be B. D is the depth of the least cost solution. So if there is a solution somewhere in this tree, D is the depth where that solution exists. And M is the maximum depth of the state space. It's possible that that state space could be infinitely deep for a number of reasons. For example, there might be loops. If we go back to here, notice that at this point here, from Arad we've gone down to Sibiu. One possible option open to us is that we go back to Arad. Now, any sensible agent would not do that. That would be a pretty stupid thing to do, because you will have just gone back to where you started from, and you'll be in exactly the same situation as you were before you even started, except having used a whole lot of fuel and a whole lot of time to get to Sibiu and back to Arad. But a dumb agent wouldn't necessarily know that, and could just keep looping infinitely. And we talked about this in the last lecture, the moth that flies around and around the flame. Okay, so we're not going to have time in this lecture to go through all of these. Some of them are relatively simple. I'll go a little bit slow at the start and maybe speed up, and then I'll pick up when we hit 2 o'clock. I'll pick up where I left off in the lecture on Wednesday at 1. So, uninformed strategies for searching a tree use only the information available in the problem definition. And these are some examples of uninformed strategies: breadth first search, uniform cost, depth first, depth limited, and iterative deepening. And probably if you've done advanced data structures or any data structures course, breadth first search and depth first search are probably fairly familiar terms, but I will spend some time going through them. So the idea in breadth first search is that you expand the shallowest unexpanded node. So in implementation, the fringe is the set of unexplored nodes that are effectively currently open. Then in breadth first search, the fringe is a FIFO queue. FIFO meaning first in, first out. So as you add new successors, they go at the end of the queue, so that the oldest ones, the ones that have been in the queue for the longest, are the ones that get processed next. So we start out at node A, so A gets put into the queue. And then we process A. And we process A by saying, is it the goal? No, it's not. Let's add to the queue the successors of A. The successors of A are B and C. They're added in the order B, C. And so B is now at the head of the queue, so we process B. Processing B says, are we at the goal? No, we're not at the goal, so we're going to expand B. So we expand B to D and E. So we end up adding D and E to the queue. Remember that C was still in the queue, so the queue now consists of C, D, E. So the next thing to process is C. So we process C, and processing C results in adding F and G to the queue. So the queue now consists of D, E, F, G are the remaining nodes. And hopefully, the goal is one of these states. Otherwise we fail. So that's our breadth first search. Is it complete? Meaning, will we find a solution if one exists? Yes. Why? Exactly. We're guaranteed to check every possible node in breadth first search. So we will find something if it exists. If the branching factor is finite. Okay. Time complexity. Well, it's actually pretty nasty. Order b to the d plus 1. So it's exponential in the depth of the solution. Likewise, it's very, very heavy in terms of its memory requirement. We have to keep potentially every node in memory. So the space requirements for this algorithm are b to the d plus 1 as well. Again, exponential in d, which could be really nasty. And yes, it is optimal if the cost is 1 per step, but in general, it's not necessarily optimal. Because typically we'll stop as soon as we find a solution, and so because we're going down depth-wise, if there happened to be a solution here, then we will find it at this level, having searched A, B, and C. So we won't have searched these, so we won't have wasted time getting there. So it will be optimal. The big problem with this is that it is the space requirement. So even with a fairly old CPU, we could be generating nodes at 100 megabytes per second. That could result in a tree size of several terabytes, 8 terabytes in 24 hours, if the search space is big. Uniform cost search, maybe this will be the last thing that I talk about. What we'll do here is expand the least cost unexpanded node. So in effect what we're going to do is we're going to take the same principle that we had with breadth first, we'll create a queue of nodes, but then we'll make sure that that queue of nodes is always sorted, so that the least cost unexpanded node is always at the start. And so it's equivalent to breadth first if all the step costs are equal. Yes, it's complete. This is nasty. I'm not going to go into the details of how you prove this, but basically the time complexity is the number of nodes with the current path cost less than the cost of the optimal solution. There's no point in expanding a node that has a path cost greater than the cost of the solution. And I reckon that's probably a sensible place to stop. We'll pick up on depth first search on Wednesday.
At the end there, you're saying that it is optimal if you store each depth before you use the node, right? Or do you mean when anything gets to you, it gets put into like
Which one are you talking about?
So in the same breadth first search,
Yeah.
it does get you the optimal solution if you do sort them by their cost.
Well, so if the cost is let me go back. Sorry, let me make that.
It's like the very, very last slide.
Oh, the last slide. Okay, sorry.
I believe, the one you're on, then, the last one you're on.
This one here?
Yeah, so here. Yes, if nodes are expanded in increasing order. So do you mean, like, whenever any node gets added to the queue, that gets put into like a sorting...
Exactly.
Right,
Exactly.
okay.
So you wouldn't need...
And then you just pop the loss, like a...